All right, memory system. In our current design, we've just said that you load from memory and you read from memory. And in reality, that's all you do with the memory system, but it ends up being a very, very complicated process, which we'll get because reading to main memory is very slow, so we have to figure out a way to speed that up. All right, so what we've discussed so far, you have a register file, little array of storage, 32 registers. In our Verilog design, it has about 8 registers. Memory, of course, is bigger, array of storage to hold more values. And we've discussed at least a couple ways to do it. You can do static memory with logic gates. That's where we did our flip-flops and our array of flip-flops. You can also do ROM or other ROM-like storages with diodes. They're really the only 2 things we've talked about so far. Welcome back. All right. So we have lots of memory for our processor. Well, we want memory at least. Our design, we've only used 2 to the 16 words of memory. MIPS requires 2 to the 32nd because that's how much memory you can address in a 32-bit integer. And then the latest 64-bit x86 requires 2 to the 64 bytes of memory. What choices do we have? Well, we could do SRAM. We haven't talked about that too much. DRAM. You've heard of these 2 terms, I'm assuming, when you start buying memory. So good, these aren't new. We could use the disk. I guess we could try paper. Anyone want to have the computer hooked up to paper and go and read? No. No one wants to go back to the 60s? No?
The like dot sheet things?
Yeah, the punch cards, yeah. No one wants to do punch cards? No?
They take up too much room. Such a waste of paper.
Someone has to keep the lumber industry in business.
That's what houses are for.
Yeah, but that's just one time. It's not, once you have the house built, you're not going to...
Yeah, but with the way people are repopulating the planet, houses are just going to keep popping up all the time until we run out of space.
And then what do we do?
Apocalypse.
The moon?
Then either A, removal of warning labels and natural selection will take its place, or B,
I was
we gotta
waiting for
figure
that.
out how to colonize other planets.
Wait, what'd you say?
Unfortunately, we may have a less than good solution brewing somewhere on the planet. Less than good. Less than stellar. Yeah.
Apocalypse.
An apocalypse. All right. All right. Well, that's great, guys. Thanks.
Glad that's
You're
on
welcome.
recording.
All right. Let's go look at this graph. Just see what it's talking about. This is the point of this graph is showing you how memory has become cheaper and cheaper, exponentially cheaper. Oh yeah, I forgot which chapter this is in the book. It's the memory chapter. Which one is that? Go to the table of contents. Look up memory.
I tell you what, those prices are going back up. But yeah.
You're going to guarantee it?
Well, they already are. Super expensive. To get a solid state drive, like a 5.
Oh no, that's not memory. That's something different. Well, I guess in a way it's memory. I'm talking about
You
RAM
said
right
SSD
now.
on there.
The memory chapter?
It's either 2 or 4.
Can you have solid state RAM?
Bring me to the memory.
You can use the solid state hard drive as RAM if you want to,
Not as fast.
but that's
Exploiting memory arc?
yeah. You got memory.
That's 5.
Okay, so we're on chapter 5. Exploitation begins in chapter 5. All right. All right. The point of this is to look at how prices have over time. Over here, you have the price per megabyte. So we're comparing it per how much it costs to buy a megabyte, so to speak, of whatever. We go back to 1955. We all remember the 50s. And this one goes up to 2015.
Remember it like it was yesterday.
So notice a flip-flop would have cost a ton, a lot. What is that? 10 to 9, so that's a billion? Yeah, no one's got that. Well, maybe. A billion and 55 bunnies is not good. But if you watch this graph, let's see, when did Sims come out? So Sims are the little guys right there. We went to DIMMs pretty quickly. And then you got some big hard drives. Oh, big drives. Notice the big drives are old one. Those were usually up to a meg. And by big, I mean like
Oh.
Oh my
big.
god.
Like big.
I like
Not
small drives.
small drive. Well, yeah, because then you had a hard drive. Well, you think of hard drive is pretty small. And then you have flash sticks and, of course, SSDs. So things are getting pretty cheap.
I like where the first one appears. It's like way back when. And then you got like another one where it just like skips like 10 years.
Just like, here you go.
That's so good. Hey, but y'all remember floppy drives, right?
Yeah.
Yeah.
Sure.
What's that?
I think we have one somewhere.
What do those do?
The floppy drives?
It's memory.
It's a
It's a disk drive. So before hard drives, you
It's
would
like
you
it's
take your
like
floppy
USB.
disk, put it in there, click it, and then run your software from it. So the first ones held, was it 64 kilobytes or something?
Oh, that's so
And then the
adorable.
latest, I think the latest one, the biggest they got was 2.8 megs, if I recall correctly.
That's cute.
So is that like
That's
a
very
flash drive
cute.
before a flash drive?
My external
Yes,
hard
except for
drive
it's
is 2
actually, you can open it
terabytes
and it's a
now.
disk inside of it, and you have to have a magnetic head to read it. So it would go
Here's the video I should try to show.
while you're trying to read it. I guess y'all never knew the joy of floppy disks.
We didn't really use them. They were gone by the time
Yeah.
we were born.
I mean, I saw them around the house, but we never ever used
Yeah.
them.
If I was rummaging through a drawer, occasionally I came across one, but I never used it.
Never put it in.
I was like, ooh, what's this thing?
If you think
I didn't know
flash
how to
drives are
use it.
slow, you haven't seen nothing yet.
Can any
Oh,
computers now
no.
run with a floppy disk?
Yeah, well, they have USB to floppy drive converters.
Interesting.
Oh yeah, they got it.
So, let me see if we have any at the house.
More what? Inefficient?
Inefficient.
Then I can tape. Because at least with a disc, you can move the head up and down and randomly go to something. If you're at the end of a tape and you need to go and read something from the
Oh
beginning,
my god, like a VHS.
yes, it's a
Oh
VHS.
my,
Yeah.
that is so annoying. And when somebody puts back the movie without rewinding it first, and so you have to rewind.
Please be kind and rewind.
Yes, and so you have to rewind it, and then
Blockbuster.
you've already seen the whole movie backwards, so you know what happens.
You don't have to watch it. As
We
a
used to
rewind.
cut the TV
Yeah, I
off
know, but
While it was
and then
rewind.
rewind it.
That's a good idea.
Wow.
Use that in the
All right,
future.
good times. So
When we used
things
to
have gotten
VHS.
faster and cheaper
VHS is a
exponentially.
good
Well,
comeback.
they've gotten cheaper exponentially. They have not gotten faster. It looks linear, but notice the scale is logarithmic, which means a
Touche.
linear graph is exponential.
It's confusing.
No, it's. Why would you even say that? That's actually great. This is good. This is wonderful. That's why things get so
I want it
cheap.
to be curved.
Oh, you want curves. Well, if you
That's
did,
gross.
it would go.
Yeah.
So you like cliffs, jumping off
Yeah.
of cliffs.
I wanna go-
Okay, anyways.
No.
Option 1. We'll use
You know, I started
SRAM.
diving. I did that.
Has about 5 to 10 nanosecond access, so a little slower than our flip-flops, but still pretty quick. The decoders are big, the arrays are big. It's going to cost a lot of money. All right, this is about 5 years old, so sorry. It's about $7 per megabyte.
You know.
What?
It's just, it is old. I was laughing about that.
Oh, yeah, it's all. Oh, I forget. I'm so matter of fact. Yes. So it cost about, what is that? 43 cents for our design, which is not bad. It costs $28K for MIPS. Probably not a good thing. And then I have 123 trillion for x86-64.
Imagine how
Don't
much
do it
a
that way.
computer would cost.
Yeah, that's how much your computer would cost. Yeah,
Yeah,
that,
totally can afford that.
all right, not doing that. Let's
Pocket
try a
change.
DRAM. It has an interesting system. Hopefully, I'll put up a slide there where you save a bit in a capacitor, and the capacitor basically holds it for as long as possible. What?
Hopefully you'll put up a slide there.
Yes, because I just realized there's no slides on DRAM right now.
Nice.
Notice it has 100 nanosecond access. So is that faster or slower than DRAM? Remember that slide 10 seconds ago, Sydney?
No.
So fast.
It is faster. No. It's slower.
I have no idea.
5 to 10 nanoseconds versus
So
100
SRAM's
nanoseconds.
5 to 10 nanoseconds. This one
That's
costs
slower.
100 nanoseconds, so it is slower.
slower.
But
About by a
more
factor of
cost-efficient.
at least 10 times slower.
It only costs 1 trillion.
Well,
it's
build a
$60
fast.
per gigabyte.
Well, the problem here is that if we run it at gigahertz, that means each gigahertz about a nanosecond. It would take 100 clock cycles to get something from memory. Right.
Sit there and wait.
Right. So you could you'd have a processor that just basically stalled forever on a load. Well, let's at least look at the cost. $68 per gigabyte. I would say that's probably down to about 20, but we're gonna stick with this for now. Less than a penny for our design. It's great. Yes, that's good.
Yes.
Give me half a penny.
272 for MIPS. Okay, not the best, but it still work. It still work. 1 trillion for
Yeah.
x86
Look how cheap.
I love the.
It's better than 128 trillion.
Yeah. What's
I
that?
love the jump.
We better jump on these prices.
Yeah, I know. Well, it's still good, right?
Pocket change.
All right. We could build it using disks. So if we use, and this is spinning disks, not SSDs. It would take 10 million nanoseconds, which means that we would have to wait 10 million clock cycles to read something from memory.
Nice.
The joke here is Intel 4004 was the first x86 processor, so we might as well just have stuck with that thing because if it could take 10 million cycles to get anything, you know, why would you want anything faster, right?
Right.
Costs are at least reasonable, 25 cents per gigabyte. Actually, it's probably cheaper than that now. How much does a terabyte cost?
Like
$100.
No, not $15.
I mean,
$25.
no,
No, I think it's more like
100
50 or
is
something.
probably 2 terabytes.
Oh yeah,
It's like 80 to 100 for
Yeah.
2 terabytes. It's
Specific.
probably, it's probably
Just keep throwing that out.
It's 40 to
It's literally
50.
25.
It's
or
for-
It's
yeah, it's 40 to 50.
$44.63.
All right, so this is
Two
probably
is 100.
probably about a penny, less
Yeah.
than a penny for a gigabyte.
Yeah, 2 is
So
100.
basically free for our design. Yeah. $1 for MIPS. All right, that's not bad. That's good.
$25.
4 billion for our other machines. Well, you know, at least now, the federal government can afford it, right? Maybe.
No.
Just
With
add
what
it to the
money?
dead pile.
With the
We'll
what
figure it out
money?
later.
Anyways, Google can afford it.
There
right?
you go.
Google can afford it. There we go.
And Disney.
And
And
Disney.
Because Disney can do whatever they want.
All right. So what's the problem here?
They're their own government.
Yeah.
It
It takes forever.
takes forever, but it's still not as cheap, and it's still not as cheap as we need it.
Yeah.
So we want a memory system that runs at clock speed, about 1 nanosecond access. Oh, we're so demanding. We want a system that we can afford, maybe 25-30% of total costs, which again is not anything. Options 1 through 3 are way too slow. And option 1 and pretty much 1 through 3 are also way too expensive. So
Option 4.
we're option 4, right?
Is it
That's
cash?
that's the only solution.
Cash.
Right. Thank you. Yeah, there you go.
Oh, yeah.
Gotta get these words out. Yeah.
That's weird.
Use a little of everything wisely. Remember, small is fast and cheap, big is slow and expensive. So use a small array of SRAM. So small means fast, it means cheap. Then use a larger amount of DRAM for more memory, and use a really big amount of disk storage. Also, don't try and ever buy 2 to the 64th of something. That's how much you would need for 64-bit. It would take forever to format. Anyway, do you really need that much data? I don't even know how much trillions that would, how many terabytes that would be, or
Totally
petabyte.
need that much.
For what? You can't even, we don't have that much
Anime.
data to store.
Anime. All of the
No,
seasons.
what you would, I mean, yeah, so
Movies.
the solution here is use a little bit of everything.
Yep, that's what we need. Storage.
What do you think he was going to say,
Nothing.
Jonah? Please.
Nothing.
Okay.
They won't
Me?
continue.
Why are you so red?
I'm fine.
Are you sure?
Yeah, I'm good.
I'm trying to teach here, Jonah.
Sorry. I apologize.
If you want to heckle, that's great, but be loud, okay?
Okay.
All right.
So we can hear it later and laugh at it.
Yeah, I don't mind the hecklers. All right, so we're going to use a small array of SRAM for the cache, which we're going to hopefully be for most accesses. Then DRAM for main memory, and then disk for virtual memory. And again, don't try and buy 2 to the 64th of anything. I forget how much that is. It's a lot.
It's
least
apparently
for a while.
18 million terabytes.
18 million. Oh, so it'd be 18 million terabytes. What
Yeah.
would you do with 18 million terabytes?
Movies.
I would think we had.
You can download one game off
I
the
would
Xbox.
sell 18 million
My
terabytes.
God.
Wow.
They're so bad.
All right. So here's the famous memory hierarchy. Well, y'all don't have the food pyramid anymore, do you?
No.
Y'all didn't have the
Wouldn't
food.
you also
What
have
is it now? Is it a plate now, I think?
I mean, it's not
Wait,
just me
yeah.
that has it. You would have it too, right?
Yeah.
I had the food pyramid. Oh, y'all still have
We
the food
had
pyramid.
I
we
mean,
had
If
it.
you have it, then I have it.
Now
Okay,
now
We
they
both
have
have it.
I think it's a plate.
Is
For the food.
It makes no sense.
I think it's a
Whatever.
plate. I'm pretty
The
sure.
food pyramid was already a little dumb, and they just took it to the next level of dumbness.
Yep.
Anyways, I'm not.
Extra dumbness.
It's not a pyramid. What is it, a rectangle?
No, it's a. I think it's a
circle.
plate.
It's a plate. No,
Yeah,
it's
they
like
have
a.
like sections of the plate. It's like this is how much
It makes no
protein
sense.
you should have. This is.
All right, so at the top, the cost. Well, I don't know why they have cost increase. Well, cost per megabyte is fast, or is
What?
expensive. I'm sorry.
Retry that. It's fast.
The cost is no. The access. is
There we go.
fast. The cost is for.
Expensive.
Well, it's expensive for a large amount, cheap for a small amount.
There we go.
And then latency takes the river down here, not much time up there. So the top one, small, fast, bottom one, big, slow, main memory somewhere in between. All right, everyone got that ingrained? Welcome back. All right, rehashing our terms. Let's, we get the word architectural and non-architectural confused a lot. The architectural view of memory is it's what the machine language sees, which is literally just a giant array of storage. You give it an address, you read from that word what's in that address, and if you want to write to it, you write this data value to that address. That's all it sees, architecturally speaking. What we are adding is something that's non-architectural, because we can make up memory with SRAMs, with DRAMs, with disks, with paper and pencil if we wanted to, as long as we adhere to the architectural standard that we had. In other words, the machine language, aka the program, has no idea what's happening underneath the hood. It just cares about reading and writing to memory. The nice thing about this is a new implementation will not break it up, will not break your current code, which is what we want. All right, so the cache will hold the data we think is most likely to be referenced. If you remember back here, up here is fast. So when we read and write, where do we want it to be reading and writing? Up here in the cache, because down here is way too slow. Just to drive home what this is going for, we're going to do an analogy. Let's pretend that you're hungry. Everyone, can everyone at least pretend that?
I'm always hungry.
You're always hungry?
Yeah.
So,
Right now.
option one, actually, I like option 0 first. Option 0 would be if there's food right in front of you, then you just eat it, right? You're good to go.
Yeah.
That'd be if you had your memory in the register file of our processor, like what Sydney has right now. Okay, good, thank you. But if you don't have food in front of you, where must you go? To the refrigerator, right? Yeah. So you find something, eat it. Maybe your latency is a minute, right? Because you got to go. You have to get up. Stand up. Yeah, I know.
Ah,
man.
what?
Yeah, I know, right? You gotta stand. You gotta walk over.
He's had
Unless you
wheels.
have a rolling chair.
Or a
But then you
robot.
also have to open the door and make sure you don't smack your roommate while you're
Robot.
opening the door.
Your
Nope, smack
robot
'em.
can get it for you.
But that still takes time, right? Because you gotta go,
then you
okay,
don't have to put the-
all right, Caitlin, I'm going, and then he trips over something and you have to fix him, right?
You wouldn't or
Or you train a dog.
And train a dog. Anyways,
I'm gonna do that.
we'll say it takes a minute, all right?
Okay.
But it's actually not that bad because if your refrigerator is empty, what do you have to do?
Go to start.
Go to the store.
You have to go.
Gotta be in a gotta be
Or
in a
you have to
hole.
close the door, lower your expectations, and then reopen the fridge door. That's what I do.
So you go to the store, now you gotta find something, buy it, take it home, and then eat it. Or maybe you eat it in the car on the way over because you're really, really hungry. Anyways, we'll say that takes 20 to 30 minutes. A lot longer,
like an
right?
hour.
This is not just, not just twice as long. Or small percentage. We're talking factor of 10, so 30 times longer. All right, but if it's not in the store and it's not in the refrigerator, right? No. You got to work with the analogy. But you really, really, really wanted this specialty food, and the store will not order it. You have to go
Online.
Online. It doesn't
Amazon.
exist.
It doesn't exist. Well, then you
But the
push that
seeds for it do. So you have to buy the seeds, plant it,
You would
Get a new
starve by
craving.
the time.
wait for it to grow,
button. Get a new craving.
You might as well just eat the seeds.
And then maybe in 6 months you can have the food that you really, really want. The point of this is that this is the L1 cache, this is main memory, and if you ever have to go to disk, that's like having to grow your own food. That's how bad going to
I would
disk
just
is.
tell my kids fresh out of luck.
Okay?
You won't starve tonight.
So which of these three do we want to avoid at all costs?
Option
Go,
one.
go, okay. What?
Option one.
You just throw away the refrigerator whenever you're hungry, go to the store?
Yep.
No, you didn't even mention the fact that it could be just be in the snack cupboard. All you have to do is walk over to a cabinet and open
So
it.
that would be like a victim cache, which we have.
Nowadays you have those smart fridges that are like, oh, you're almost out of milk, and they order you milk.
Oh,
and then
yeah.
It shows up at your doorstep.
That's nice, isn't it?
Yes.
That's crazy.
So now we're down to like 1 minute again.
But what if that broke and you have to go to the store? Oh!
Sadness.
Lower your expectations.
Okay, so let's throw some numbers in here. These numbers, actually the first two numbers are pretty close. This number would be a lot larger in real life, but let's go ahead and stick with it just to see what the numbers come out. So we're saying if you go to the cache, what? Come on, louder.
I can really talk. You need to do it.
I'm not singing it.
Oh my
singing
God.
Bohemian Rhapsody.
Oh yes, Bohemian Rhapsody.
Yeah, I said, is this the real life or is it just fantasy?
No, this is real life. So we'll say going to cache takes 1 cycle, going to memory takes 100. In reality, this number is probably closer to 500 cycles. And going to disk, 10,000, it's probably closer to 1 million nowadays. Well, we'll stick with this just for now. What's the average access time for 100 memory references if you measure that 90% of them go to the cache are hits and 80% of the accesses to main memory are hits? Okay, this is how you approach these problems. When you're going to read something, it's going to first go to the cache. If it's not there, it'll go to main memory. And if it's not there, it'll then go to disk. Okay? So, first off, we need to calculate of the 100 memory accesses, references, how many go to the cache? 90, because you have 0.9 times what, 100?
Yep.
Okay? So that's main memory. How many go, I'm sorry, that's cache. And then of main memory, well, 80%, after the cache, 80% of them go to main memory. So how many, first off, how many references are going to be going to main memory? 10%. Yeah. Right, 10%.
80% of the 10%.
Yeah, so you have 0.80% of the 10% of the 100 go to main memory. But how long does this take? 100. Right? So that's 100 cycles. This only takes 1. I didn't write it there because when you multiply it by 1, who cares? Okay, and then what's left over?
2.
Well, the 20% of the 80% of the 10%, 0.02, right? So 0.02 times 100 times, what is that, 10,000? All right, so we whip out the calculator. This is what, 90?
90.
Okay.
That's 800.
800.
And that's 20,000.
What's the dominating term? Even though 2% went to the disk, he still dominates basically your average access time.
Sadness.
Yeah, 90% went to the cache, yet our average access time was basically determined by how often we had to go to disk. This is to help you understand the magnitude of the numbers here, of why it's so important to avoid disk at all costs.
Especially if, like you were saying, nowadays it's even bigger than 10,000.
Yeah, it's even bigger than 10,000.
In applied networking, we have to like calculate like cache stuff like
Oh,
that.
here we go.
Cache.
So, some real numbers. All right, I really need to update this to the PS4.
Wow.
That's
I
really,
keep-
that's really
Shade thrown.
The PS3? No, that's not old.
Do the I-9.
This is 4th gen. We're up to 7th gen. It's not that bad. There's a 9. Actually, these numbers have increased. That's a problem. If I keep looking these up, these numbers are just getting worse and worse and worse. But for i7 4th gen, the L1 cache, because you can have different layers of cache, 4 cycles, and it's 64 kilobytes. 10 cycles for L2, 256. L3 is between 40 and 300, and then main memory is 540 cycles. So it's even worse than beforehand. The PS3, I love this one because it has the weirdest architecture I've ever seen. It would take 4,000 cycles to go to main memory. So what does this mean?
Don't use main memory.
Don't use main memory. I didn't even look up how much the disk took. It was way more. But hopefully you can see. What does this mean? We want everything to be in the L1 cache, right? If you can't be in L1 cache, it better be in the L2, because we don't want it to be in L3 or main memory, and then so forth and so on. But notice that by adding layers here, you can they add let's see, they can capture more faster. Because notice that when your cache increases, the amount of storage you can hold increases as well. So hopefully more of your accesses can fit in the L2 instead of going to main memory. All right. Okay. So so why is matrix? So why did that matrix multiply thing get sped up when I did blocking? What was I doing?
Accessing cache
Accessing cache, correct?
instead of memory.
Right. Think about this. We had, on this example, L1 is 64 kilobytes, right? My machine, it's actually 128 kilobytes. By blocking it out, by blocking it, basically taking each small chunk of these three small chunks, make sure they all fit in the L1 cache. I'm making most of my memory references in the fast one, as opposed to if I run outside the block, I'm constantly having to go back to main memory instead of keeping it within the cache. So that's a little, hopefully a better picture of what's going on. I will present that a little better one day. Don't worry, I have the slides for that.
One day.
You know what's coming. Okay, let me pause here before we start talking about cams.